One of the things about bonding theories like Lewis theory is it helps us to predict the shapes of molecules. So we're going to use something called valence shell electron pair repulsion theory, VSEPR. You can't really pronounce that very well, so we kind of switch the S and the E. We call it VSEPR theory, VSEPR, valence shell electron pair repulsion theory. And this is the idea that electron groups repel each other. They're going to try to move away from each other in a molecule. And by electron group, we mean a lone pair, a single bond, or a multiple bond. So a double bond is one electron group. A triple bond is one electron group. And the repulsion between the negative charges of the electron groups is what determines the geometry or shape of the molecule. So if we look at a simple molecule like carbon dioxide, this is the Lewis structure. We have to look at the Lewis structure before we can predict the shape. So we look at the Lewis structure and we see that the central atom, carbon, has one double bond with this oxygen and one double bond with that oxygen. And so what we're looking at is the central atom, and we're asking ourselves how many electron groups are on the second central atom. Well, there's one double bond, that's one group, and here's another group. So the way these two groups get away from each other, remember molecules are three-dimensional, they're going to go on opposite sides. So you could imagine if this is the planet Earth, and this is you, and this is that X who really just jacked you over, and you really hate him or her with a passion, and you're going to get as far away from as possible from them, and so you're going to live on the other side of the Earth, right? Getting away, repulsion, right? So when there are two groups, they will go to opposite sides of the central atom, and we get a linear geometry. These three atoms fall in a line. And we talk about bond angles, and we're talking about the angle between these two atoms with the central atom as that apex. And so this angle doesn't really look like much of an angle. It looks like a line, because it is a line. The angle is 180 degrees. Any questions about that one? Let's look at H2CO. Here's the Lewis structure. Here now, the central atom has how many groups? 3. One single bond, another single bond, and a double bond. That's 3 groups. 3 groups are going to get away from each other in what we call a trigonal planar geometry. So this molecule is also flat, and the 3 groups are going to spread apart, and they're going to form a triangle. And the angles will be 120 degrees. When we get to something like methane, which has 4 electron groups, there's carbon, and it's got 4 single bonds to hydrogens. We've got 4 electron groups. When we draw this, it looks like it's going to be a flat square. Then the bond angles would be 90 degrees. But it's not limited to 2 dimensions. And it actually makes a 3-dimensional structure called a tetrahedron. It's a 3-dimensional shape that has 4 sides, tetrahedron. It's like a triangular pyramid. And by doing it this way, it can get angles of 109.5 degrees. So a tetrahedron is a geometric shape with 4 triangular faces. A cube has 6 square faces. So it's like a step down from a cube. Well, if we look at something like ammonia, ammonia has 3 bonds and 1 lone pair. The lone pair is an electron group. It repels the other electron groups. And so we get a tetrahedral shape. But now one of the corners has a lone pair instead of an atom. So if we look at the electron geometry, how the electrons are arranged, it forms a tetrahedron. But if we look at the molecular geometry, we're not looking at the electrons. The electrons are too small. we're just looking at the atoms, then it's like we've got this tetrahedron, but this top part's invisible. And so what's left is this shape, and that's triangular, but it's not flat. So it's called a trigonal pyramid structure. The lone pair is important because it pushes these hydrogens closer together than if it wasn't there. Does that make sense? Looking at water, water has 2 lone pairs on the central atom and 2 bonds. So a total of 4 groups. 4 groups will get away from each other in this tetrahedral shape. I'll dig out some models that you can play with when we're working on the worksheet so you can get a better idea for the shape of this. Electron geometry shows how the electron pairs are arranged, and then when we think about the molecular geometry, we pretend that these electron lone pairs are invisible, and what's left? Well, this is called a bent structure. Isn't that a fancy name? Trigonal, pyramidal, and all these fancy names, and then there's bent. Yeah, it looks like a line that's bent. But that's water. It's bent. So this table in your book summarizes all of these different possibilities. And that can look a little daunting to memorize, right? But you don't really have to memorize it if you can think about how are the electrons spreading apart from each other? What shape does that make? And so you look for the number of electron groups. 2 makes a linear. They go on opposite sides. 3 makes a trigonal planar shape. 4 makes tetrahedral. So they're just trying to get away from each other, get as much space as possible between them. And that will give us always the electron geometry. If there are no lone pairs, the electron geometry and the molecular geometry are exactly the same. The only time the electron geometry and the molecular geometry are different is when you have some lone pairs. So here we've got a lone pair. So then we think, well, okay, this is that trigonal planar, but one of these points is invisible, and then describe what's left. So you can end up with a bent structure. So SO2, because it has a double bond and a single bond, and there's a lone pair here that's invisible, it is also going to be bent like water, although the angle's going to be a little different. Tetrahedral, if there's 1 lone pair, we get the trigonal pyramid. If there's 2, we get bent. So if you can think about it, you don't really have to memorize much of anything. Any questions about molecular shapes? So here are the steps that your book gives you for predicting geometries. Draw the correct Lewis structure. You have to start with that. Determine the total number of electron groups around the central atom. Figure out how many bonding groups and how many lone pairs you have. Then your book says refer to table 10.1. Well, that's real nice when you're doing homework or something, but I'm not going to give you table 10.1 on an exam. So, determine the electron and molecular geometries by considering how the electron groups can get as far away from each other as possible. And then if you have a lone pair, then imagine them frozen and one of them's invisible. And then what's the shape that's left? So examples, let's do Cl and O. And they're telling us that nitrogen is the central atom. So the first thing we have to do is draw a Lewis structure. And it says that N is in the middle. So I'm going to put N in the middle, and I'm going to put Cl on one side, and I'm going to put O on the other side. It doesn't really matter what side I put them on. What was the next thing we needed to do when we did Lewis structures? How many electrons? So how many valence electrons does chlorine have? 7. And nitrogen has 5, and oxygen has 6. And so that adds up to 18. So we have 18 valence electrons. So I'm going to start out by putting 2 there and 2 there because I need at least a single bond. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, we're close. Is everybody happy? No, the nitrogen's not happy. So we're going to have to do a little more sharing. I'm going to take one of these lone pairs from oxygen and share it with nitrogen. And so we're going to end up with a double bond there. Is everybody happy now? Yeah, everybody's got 8 valence electrons. That's the first step in predicting molecular geometry, is to draw the Lewis structure. Now we're going to look at the central atom, and we're going to say how many groups of electrons are around it. 3. There's a single bond here. Maybe I should draw that in. Single bond, and a lone pair, and a double bond. So here's my lone pair, and here's my double bond, and here's my single bond. 3 things are going to make a triangle. They're going to spread out and make a triangle. That's the electron geometry. The shape of the molecule, though, we make that lone pair disappear, and what do we have left? It's bent. Any questions? Let's do SO3 2-, sulfite ion. Well, we've got 1 sulfur and 3 oxygens. What's probably going to be in the middle? The sulfur, right? Yes, it's going to want to be symmetrical if it can. So I'm going to put the sulfur in the middle. Oxygen, oxygen, oxygen. Now we count up electrons. How many valence electrons for sulfur? 6. And how many for oxygen? 6. There's 3 oxygens, so it's 3 times 6. What do I do with that 2- charge? I have to add 2, because that means that this ion has 2 extra electrons. So I've got 26, right? 26 electrons. Then I'll start distributing my dots. So I'll put 1 there, a pair there, a pair here, and a pair there. Because I need to have bonds. Remember, a bond is 2 electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Nice, there was enough. What do I have to do to finish that Lewis structure? I need brackets. Because this has a charge on it, and we can't leave the charge off. So that whole thing has a -2 charge. To determine the shape of the molecule, we're going to look at the central atom. How many groups of electrons are around it? I hear these little murmurings. 4. There's a bond, and a bond, and a bond, and a lone pair. 4. Lone pairs count. So how do 4 things get away from each other? Tetrahedron. So this is how you can draw a tetrahedron. You can draw, those 2 lines are in the plane of the screen, and then there's one that's sticking out. Use a wedge to indicate that that's coming out at you, and then we used a dashed wedge to show that that one's going behind. So there's the sulfur in the middle, and then there's these oxygens. And then up here, we've got our lone pair. Those 4 electron groups, 3 bonds and a lone pair, are spreading out in a tetrahedral shape. The electron geometry is tetrahedral. For the molecular shape, we take this lone pair of electrons. Remember, electrons are really, really tiny. Even compared to atoms, they're crazy tiny, because they're tiny compared to protons. So these are minuscule. Electron compared to the size of an atom would be like a speck of dust in a really big football stadium. That's how small an electron is compared to the atom. So if I'm making my atoms this big, could I even see the electrons? No. So when we think about electron geometry, we erase him. He's invisible. He's still there. If he wasn't there, if that lone pair wasn't there, this would not make this shape. It would make a trigonal planar shape. It would be flat. So he's here. He's just invisible, like an invisible person that's really no fun to have around. And everybody, you can tell he's there. Maybe you can smell him. I don't know. And everybody kind of gets away from him. We don't want to get too close to you. I can't see you, but I know you're there because you're so annoying. It reminds me of my kids. You're looking at me. He's breathing on me. Anyway. This, what's left here, before I erased that, I can bring him back. That's tetrahedral. But when I take that top off, it's not a tetrahedron anymore. This, do you see there's a triangle here? These three make a triangle. Maybe make that a different color. So there's a triangle going on here at that base. This is a trigonal pyramid. It's not planar. Planar means it's flat. So trigonal pyramid. It is a trigonal pyramid, or it is trigonal pyramidal. These are, just nouns and adjectives. This is without the lone, this is the molecular geometry. The molecular geometry, we say the lone pairs are invisible, and we're not describing this shape because we can't see them. But the lone pair is there. The electron geometry is tetrahedral.
Yes, with
That's,
the lone pair.
yeah, we're looking at where the lone pairs are. And then, yeah, it's a little bit confusing because you say, well, without the lone pair. Well, it's not without the lone pair. It's still there. It's just that we can't see it. And so we're looking at this shape. If I can scrounge some balloons up, I'll do some balloons for you, and maybe that'll help. Yeah, we did that one. So some of these geometries are three-dimensional, and it can be a little challenging to draw them on a two-dimensional piece of paper. And so these are some conventions we use. A straight line, as I kind of gave you a preview of, that means this bond is in the plane of the paper. A hashed or dashed line is going behind. It's dashed because, you can't see it like it's behind the paper. And this bold wedge line is sticking out at you. It's like jumping out at you, right? And so that's how we represent something in three-dimensional space on a two-dimensional screen. So, like if I was going to draw methane, here's the carbon, and this hydrogen is straight up, and this one is over here. All three of those atoms are in the plane of the paper. They're flat. But then there's one hydrogen over here that's sticking out at us, and there's another one that's sticking out behind. And so it's a three-dimensional shape drawn on a two-dimensional piece of paper. And we'll get some practice with that on the worksheet. Yeah, so there's an example of how the ones in your book are drawn. These look a little cockeyed to me because I usually draw my things that are in the plane. I start up and down, so these are a little confusing. But this guy's coming out at you, and this one's going behind.